Uh, Hello everyone. So we will talk about the concepts of adder circuit as I discussed in the last class. Our primary focus of today's class will be how the binary numbers are added, and how in hardware we can implement a certain adder circuit. I will actually cover a complete flow of design from the bit level through the transistor level adder circuit per bit, and then I will move to a multi-bit adder, how we can design a multi-bit adder. For that, actually, let me ask you, whatever number that we use in our day-to-day life, like decimal number, any decimal number. For example, 259. Why do we call it a decimal number? If I ask you, why do we call it decimal number? We call it decimal number because in each place of the digit here, there are actually 10 number of digits that are possible, from 0, 1, 2, 3 to up to number 9, right? So in each of these places, we can actually think of 10 digits. And that's why it's called a number, which is a decimal number or a 10-base number. It can be expressed by this notation as well. So let's say hypothetically, you think of something. Okay? What is the why 10? Why cannot we express another number by a different basis? For example, we can think of it in 8 basis. That means we can only have 8 different digits in any of these places, like 0, 1, 2, 3, 4, 7, right? Why not that? Or why not, let's say 6? So actually we can. That's what I'm trying to put here. We can actually express any number on the basis of any integer number or discrete number. By the way, 10 is uh, 10 is the common basis that we use in our day-to-day life. That's why it's called a decimal number, or sometimes we don't express the basis because every one of us know, right? This is basis of 10. But in computer, actually, we work with binary numbers. We work with binary numbers. That means in a computer can recognize either 0 or 1. Either 0 or 1. That means any number we give in the computer, in any of the digits, we only have two options, 0 or 1. Okay. So let's say 1101. This is a number computer can recognize. And I am not saying it is 1101 in decimal. No, it is not. Actually, it is something else. It is actually 13. It is actually 13 in decimal. But we will go ahead and see how this is 13. But just to let you know that any number that have only 1 and 0, computer actually recognize ones and zeros only. So whatever number, let's say we want to give an input in computer like 259, we cannot we can give an input through our keyboard 2, 5, 9. We have different number pads, but eventually computer actually stores it. Computer actually processes it in binary digits. Each of these digits are converted to a number that is the basis of 2. That means in each of these places of digits, we have only two options, zeros or ones. So how we can we already are very familiar with decimal numbers. I hope we all are actually, but how we can actually convert our familiar decimal numbers into binary numbers that computer can store and process. So for example, if I tell you we have a number which is 259, do we have the okay. So let's think about 259. if I ask you, tell me the digits of this number, you can readily go ahead and tell me, okay, the digits are 2, then 5, then 9, right? So another way you can actually program it. If I tell you, okay, program it, like I will give you a number 259, write a program that tells me that these 3 digits separately. What can you do? Think about it. It's you can just go ahead and divide it by 10. Okay, if you divide it by 10, what is the remainder? If it can be divided by 25, then we have 250. What is the remainder? Remainder is basically so it's 25 is the result and 10 is the 9 is the remainder. Then if we divide 25 by 10, we have 2 in the result and we have 5 in the remainder. So think about it. Now, if I go ahead, you see, we have actually separated these 3 digits. You see, 2, 5, 9. So, since it's a number which is on the basis of 10 or a decimal number, we can divide it by 10, and the remainders actually tells me that what are the digits, right? It separates out the digits. So there, similarly, we can actually do it for the binary. So if I ask you, okay, we have a number, let's say we are expressing it in decimal. For example, 30, or let's say 131. I'm just giving you an example. So if I want to express it in a binary number or a number which has a basis of 2, what this is, what this will be. So for these two actually, for getting the result, what you need to do, you need to divide it by 2. So if you divide it by 2, that we have what we have here, we have 65 and 1 remainder. Then we have, if I divide 65, we have 32 and 1 remainder. Now if I divide 32, we have 16 and 0 remainder. Then if I 1 second, if I, let's say what if I just 80, then 2, what this becomes 40, then again 2, then 20, and if I divide again 1, 0. If I divide 1, then it basically it doesn't go, then we have 0, 1, right? So we can actually stop whenever we get 1, we actually can stop. Now go in this direction, like what is the number? 0, 1, 0, 0, 0, 0, 0, 1, 1. So this becomes 0, 1, 0, 0, 0, 0, 0, 1, 1. Okay. So this is actually like the decimal number. If I say 0 to 5, it's basically 25, right? In a decimal number. Like here as well, you don't have to put a 0 at the leftmost digit, because it doesn't give you anything. So this is the binary representation of the number 131. Okay, this is the binary representation of the number 131. So we have a higher number of digits, right? How many digits do we have? 1, 2, 3, 4, 5, 6, 7, 8, right? We have a much higher number of digits. So, okay. So why is that? Because now we have a basis which is much lower, right? We have, let's say, a basis of 2 in the numbers. So that's why we need a higher number of digits here. So yes, that's how we can easily convert a decimal number into actually a binary number. Yeah. So yeah. So if I now give you any decimal number, you can easily convert it to a binary number, right? That is really easy. Just divided by 2 and what is the result and the remainder. What is the division result and the remainder? Put it this way. And when you get 0, 1, 1, you already know that it's already done. So just take this direction from your right to left. So this is your most least significant number, like the rightmost number, and then this is the leftmost number. So this way you can actually convert any decimal number into a binary digit. Now we know that yes, computer can store in binary, and how we can obtain such a binary number from a given decimal number. So how actually computer computes with these binary digits? Okay. So what we can do, what computers do is actually acts in the same way. It acts in the same way. So just to give you a heads up of first few decimal digits. For example, 0, 1, 2, 3, 4, 5, 6, 7, right? Think about it. These are the decimal digits. Now I am just giving you a scope of thought that you can think of. Like, okay, what is 0 in binary? 0. What is 1 in binary? 1. But what is 2 in binary? It's not 2. That's we are pretty sure of. But what is 2? 2 is basically if you convert 2 and what this gives you? 0 and 1, right? So no. If you give 2, the result is 1, but remainder is 0, right? Result is 1 and the remainder is 0. And whenever this comes, this is your end of binary conversion. So 2 is basically 1, 0. What is 3? Divide 3 by 2. What does it give you? 1, 1. So 3 is basically 1, 1. What is 4? Divide 4. Then we get 2, 0. Then you can divide 2 once again, which is 1, 0. So 1, 0, 0. You see? 1, 0, 0. So 4 is basically 1, 0, 0. If you do the same with 5, you will get 1, 0, 1. 6 will be 1, 1, 0. 7 will be 1, 1, 1. And if you think of 8, it's 1, 0, 0, 0. So actually now if you look at the binary numbers, think of its progression. Like now at first 0, then 1. Then it goes to double digit. After 2 numbers, it goes to double digit. 1, 0, 1, 1. Then we cannot actually increase it any further. Think about it. It is 1, it is 1. So there is no place we can increase. We need to extend the number of bits. Okay, now we have 3 digits. 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1. See? This is how they progress. So if I tell you like what is the next number of this number, like what is the next number? 1, 0, 0, 0. You can easily tell it's 1, 0, 0, 1. What is the next number? So think about it. It is 0, it is 1. What is the next number? 1, 0, 1, 0. Next number will be 1, 0, 1, 1. Right? 1, 0, 1, 1. What is the next number? So you see 0, 1, 1 is basically what? 0, 1, 1 is basically 3. 0, 1, 1. What is the next number of 3? 4. 1, 0, 0. So instead of 0, 1, 1, the next number will be 1, 0, 1, 1. The next number will be 1, 1, 0, 0. Okay. So this is how number actually progresses in binary. So what we can do now is we can see how we can do some addition in binary. Let me actually tell you. How we can do the addition. So for example, think about it. if I add 0 and 1, think about 0 and 1 in binary. I am asking you what is the result of 0 and 1? Adding 0 and 1. 0 in binary is 0. 1 in binary is also 0. So if I add, then it will be basically what? 1. If I add, basically 1 plus 0 is 1. I am not writing it because you already, I think, know that basically it's the same. The order doesn't matter. So if I add 1 and 1, it will basically 2. But 2 in binary is what? 1 0. Okay. So 1 plus 1 is 1 0. What is 1 plus 1 plus 1? 3. So what is 3 in binary? 1 1. Right? So this way you can actually think of like what is 1 plus 1 plus 1 plus 1? 4. What is 4 in binary? 1 0 0. So this is how the addition happens. However, I want to show you how two large numbers are added. These are like the small ones. Now you know what this means. If you did not know how binary works at all, then it will be really surprising for you. Like 4 1 is 100. No, it's not 100. It's what? It's 4 in binary format. Okay. So that's what I'm trying to show you. Let me actually now go ahead and see how two binary, how the addition of two binary number. For example, if I add, let's say 1, 1, it's not 11. We already know it is where it is 3. If I add 1, 1, 1 with 1, 0, 1. What is the addition result? Okay. So basically, you can if I give the math to you now, you can do it by this way. Actually, very simple. It is in binary. What is the decimal? 3. It is in binary. What is its decimal? Actually 5. So 3 5 is basically 8. Now convert 8 to binary. 8's binary is basically 1 0 0 0. Okay. So this is actually a indirect way you can add, but how we can add, do the addition inherently in binary, like do the addition in binary. So I hope you remember how we added when we were in the kid, like when we learned to add two numbers. If you remember, we add two number and we put the result here. And if we have multiple digit in our result, then the rightmost digit will be put here and the other will be going where? Here. That's what we will do for the binary as well. So how we can do that? For example, if we add 1 and 1 in binary, what is 1 and 1 in binary? 2. That is 1 0. Okay. 2. 2 in binary is 1 0. So we will put the rightmost bit here and the 1 will be added to the next digit. So now these three has to add. So what is 1 plus 1 plus 0? At first think of it in decimal way. Think of it as decimal. 2. And what is 2? 2 is basically what? 1 0. So this result is also 1 0. So we will put a 0 here. And 1 will be going where? Here. So what is 1 plus 1? You can think of a 0 here, because 0 actually at the left part doesn't add anything. Like decimal, if I say give me 0 to $5, you know it's basically $25. This 0 actually means gives no value. Like this, you can think of a 0 here if you want. So what is 1 plus 0 plus 1? It's basically 2. 2 is basically 0 and 1 will go to the next bit. And we don't have any number in the next bit. So 1 is, so we will get 1 0 0 0. Basically what we have done, we have added 3 with 5, and we got 8 in this one. So this is how we actually typically add in binary format. Let me give you another example so that the idea brushes up. Idea is brushed up a little bit. For example, if I add, let's say 1110 with 0101. I'm just roughly putting this. So 0 plus 1 is what? 1. 1 plus 0 is 1. 1 plus 1 is what? 2. 2 means what? 1 0. So put the 0 here and take the 1 here. And 1 1 0 is basically 2. 2 is basically 1 0. 0 is 1. So what we have done? We have basically added 14 with what is 5, and we got 19. If you have any doubt, what you can do, you can just go ahead and convert this 14 to binary. You will get this. Okay. And if you no, is it 14? Yes, it's 48, 4, 2. Yeah. So it's 5, so it's basically 19. Okay. So you can convert these to binary and see if these represent these numbers. Okay. So this is how we actually add in binary. Now we will try to see. Probably in the last class we have shown you how if we have a Boolean function, how we can build a truth table from it. What is truth table? Truth table is the complete array or complete result of the Boolean function. Let me actually revise the concept a little bit. For example, if I tell you that I have a Boolean function z, which is basically x and y. Let's actually move from x, y. A, B, C. Okay. A and B or C. So by today you are probably familiar with this and this. These are basically, this means and this means or, right? Now if I actually tell you to go ahead and draw the truth table of this Boolean function, how you will do that? How you will do that? So what you will do, you will make a table that has all of these inputs A, B, C. Do we have any other input? No. Do we have any other output? Yes. Then the output. All the inputs, then the output. And since there are 3 inputs, how many possible combinations of input can we have? We have 3 inputs, so we can have 2 to the power 3 number of combinations possible. If we had 4 input, we would have 2 to the power 4 combinations of input. Now we have 2 to the power 3 combinations. And what is 2 to the power 3? 8. So we have 8 combinations of ABC. Okay. So begin actually drawing 8 rows here. 1, 2, 3, 4, 5, 6, 7, 8. So this is the size of our truth table. Now, how to populate the truth table? So one way to do it is so to get all the binary combinations of A, B, C. One way is to, so we have 8 rows divided by half. We have 4 rows, right? If we divide 8 rows by 2, we get 4 rows. Now add 4 0 here, 4 1. Now for the B, divided by 2 again. If we divide 4, we get 2. We divided 8 by what? 2. We get what? 4 0 4 1. Now we divide by 2 even more. 2 0 2 1 again 2 0 again 2 1. Now we divided last one even by 2. So we have 2 2 2 2, right? Now we divide by 2 again. So 1. So 1 0 1 0 1 0 1 0. It is a very fast way to actually write your truth table. Otherwise, you know, okay, what combination have I written? What have I missed? Now you cannot actually miss. If I give you, okay, write a truth table of the 5 input. Let's say I have another 5 input. Who knows? In my Boolean function. Your truth table will be 32 wrong. You will not miss if you follow these rules, like half the number of rows and insert half 0, half 1, half 0, half 1 this way, and divide it by 2 again. We will move to the next input this way. So go ahead and repeat the video, and you will know that actually this by this way you can actually build the truth table of uh, any Boolean function. Now going back to our Boolean function. What is the truth table here? So let's think about it. If now go ahead and put the zeros here. 0 and 0. What is 0 and 0? 0. And 0 or 0. What is 0? 0. And if you try each of this combination, you will see that you will get 1 here, you will get 1 here, get 1 here, you will get 1 here, and you will get 1. Okay. So these are the combinations you will get 1, otherwise in other cases you would get a 0. Okay. So this is the way I already showed in previous classes that how you can construct a truth table. Now, if I give you a challenge that is completely opposite, for example, if I gave you the truth table, not the function, and I told you to write the function instead, like this, how would you do it? So let me tell the problem again. If a truth table is given for a Boolean function, what is the procedure we can write the Boolean function? Okay, so this is how I will try to do today. So what my target is, we already know how a adder works, how we add, right? How we add binary digits. Now what we will do, we will construct a truth table for an adder. Now from the truth table, we go to the Boolean function of that. And you already are familiar with the gates, AND gate, OR gate, NOR gate, AND gate. You can easily construct a gate level circuit if I give you the Boolean function, right, from the last classes. So our target is to build a adder hardware today, and from the truth table. So let's go ahead and try to build a truth table. Okay. Yeah. So now, how we will actually build the truth table of an adder? So any two binary numbers. For example, if I want to add these two binary numbers, okay. So think about it. Now we know how to add two binary numbers. So if I want to add these two numbers, just the first bit, okay. we are calling it LSB. Okay, least significant numbers or LSB. So let's uh, forget about it. Let's think like how we can add two numbers. So let's say we want to build a block, right? We have to build a block, and in this block we are giving two binary bit. Let's say we will give 1 and 0. We will design the block in such a way that it gives me a result that I will put here 1, and another result. If let's say you already know, think about the second digit. If I add 1 and 0, what we will get? 1. But if I add 1 and 1, we will get a 0 here and 1 here, right? So think about it. You will have a number that you will put here in the result, and another one that is passed to the next binary bit. So in your block, you will definitely have two output. I am repeating again. You will design a block that can add two binary numbers. Let's say two binary bits. Now, obviously, when we have 1 0, we will have 1. When we have 0 1 here, let's say in your block, the block will give 1. But when your block has 1 0, the output result will what? Be what? 1 0. When we have 1 1, what is the result? 1 0, right? So you will basically need two outputs, right? One output like you will put here, and another output will be moved to the subsequent digits. So now, what about the next? So if you build a block like this, which has two input and two output, we will call it a half adder. Half. Why we are calling it a half adder? I am actually explaining it now. Think about the next digit. Okay. Let me erase it again. And so think about it. In the first bit, we are adding 1 and 1. We have, if I add 1 and 1, what do we have? 1 0. So we will put the 0 here, and the 1 will be moved to the next section. Now, if I want to build a block, let's say, will this block be able to add the next binary bits? It cannot, because it only has two input. But the next binary bits has how many inputs? Actually, it has two inputs, like 1 and 0. But this one is coming from the previous output, right? But it only has two pins. That's why it is called half adder. The thing that I have just shown, a half adder doesn't have an option of adding this number from the previous bit. Okay. But for the last bit here, think about the here. Do we have any number from the previous bit? No, because it is the least least significant bit, right? It is the least significant bit. That's or the rightmost bit. That's why it can add the last or the rightmost binary bits. But for the next subsequent bits, for example, here, for adding this, we need another block. We will call it a full adder. So what does a full adder look like? A full adder has three inputs instead of two inputs and two outputs. So I have already put the, I will directly go to the full adder now, because if you understand the basics of full adder, you can definitely jump to the half adder. Like the slide gives you the idea of half adder. Half adder is pretty simple, but let's go to the full adder circuit. Okay, I'm just making sure. If let's say does work again, but not sure. So let's think about how we can build a full adder circuit. How we can build a full adder circuit. So before actually moving to designing a full adder circuit, I wanted to show you that if I give you a truth table, how we can actually write the Boolean function form. If I have a Boolean function, I already know that you have the ability to draw the gate level circuit at least, right? So let's say we have a truth table like this. We have input A, B, C, and we have output here. And we have only one output, let's say Z. Okay. I'm not going to the full adder yet. I'm just showing you if I have a truth table, how I write the function. Okay. So since I have a 3 input here, we will have 8 rows, right? 1, 2, 3, 4, 5, 6, 7, 8. Okay. Now 4, 0, 4, 1, 2, 0, 2, 1, 2, 0, 2, 1, 0, 1, 0, 1, 0, 1, 0, 1. So we have all the input combinations. You already know how I have written it so fast. Now let's say our output only goes 1 here, and let's say it goes 1 here. Okay. In all other cases it becomes 0. Okay. So now I want to write a function, the Boolean function. What is the expression of Z in terms of the input A, B, C? What is it? This is my target. This is the thing that I want to do. So for example, I have probably shown you a result like A, B, C. I want to achieve something like this. Like Z is expressed in terms of A, B, and C. How we can do it? It is not AB plus C that I showed you before. It is different. But how we can get it? First task, the first step is focus or only mark the output, mark the rows that gives you 1 at the output. Mark those. We have 1 here and 1 here. Mark those first. This one and this one. You only need to focus on these two. You don't have to focus on the other rows. So, how to make your output 1 when we have 0A, B is 0, C is 1? Think about it. How to make the output 1 when you have A 0, B 0, and C 1? For this particular combination, you want to make the output 1. How you can do that? So think about it. If you have an AND gate, right? If you have an AND gate, and all the inputs, if your AND gate has, let's say, 3 input, 4 input, or 2 input, if all the inputs are 1, only at that time your AND gate gives you a 1, right? Just keep it in mind. In an AND function, if all the inputs are 1, your output is 1. So I want to write a Boolean function that gives me a 1 at the house for the Z for this combination of ABC. When A is 0, B is 0, C is 1. How we can do that? When A is 0, A naught is 1. Right? When A is 0, A naught is 1. When B is 0, B naught is 1. And when C is 1, C is 1. You see what I did? since we have A0 and B0, we have made an inversion. This is not A not, B not, C. Now make an AND function between this. Now this Boolean function gives me a 1 when A is 0, B is 0, C is 1. Right? Think about it. For all other combinations you can think of for the ABC, this function, this doesn't give you 1. This particular function, A naught and B naught and C, only gives you 1 when A is 0, B is 0, and C is 1. Like an AND function. So we have written an expression, a Boolean expression for this combination of input. That is, we are sure of. It takes care of this combination of inputs and gives a 1, right? Now, think of an OR function. What is an OR function? Or OR gate? An OR gate gives you a 1 if either of the input is 1. It is quite the opposite of the AND gate, right? If even one of the input is 1, or it gives you 1, a OR function, right? And what is the Boolean expression of OR? This. And AND Boolean expression is this. So now let's focus on this one. The another combination of input that gives a 1. How we can write the Boolean expression that gives me 1 for this combination of ABC, right? So A is 1, B is 1, C is 1. We want to express a function that gives me, we want to write a function that gives me 1 at the output for A1, B1, and C1. A and B and C. Think of it. A, B, C. If you had a 0, make a naught like this. If you like here, A naught, B naught, C. Here, A, B, C. Let's say if I work with this, but I'm not because it's 0. If I work with this, like A, B naught, C naught, right? So we have A and B and C. This gives me a 1 as well. Now I want to make a output. I want to build output that gives me 1, this and this for both. Shouldn't I go with the OR function now for these two? So let's say I have this combination or this combination. I have this combination of input or this combination of input. The output should be what? 1. Think, I am repeating again. So you have 3 input in your circuit. How many? 3. And how many output? 1. It's like this. It's like this. You have 3 input and you have 1 output. So either for this combination or this combination, you want to get what? 1. Can these two combinations happen simultaneously? No. Right? If A is 0, B is 0, C is 1, then you have a specific that combination. This cannot happen. But we want the output 1 for both of these, right? For both of these. If this happens, so this happens, we want to get what? So now, add a coordination list. This is our Boolean expression. So let me write it in this way. This is our expression of this combination. So if we had, let's say, let's say we have something like this. Instead, we have here, okay, here and here. Okay. Now let's what is the Boolean function now? Okay, that's what I want. So the table is so the truth table is given is like this now. The truth table is different now, right? We have 3, 1. So work for all the ones first. Work for all the ones. So let's work for this one. We have what? A naught, B, C naught. Okay? A naught, B, C naught. Then go to the next one. This is the another one. We have A, B naught, C naught. A, B naught, C naught. Okay. Then go to the next one, which is A, B, C naught. A, B, C naught. Now, if I tell you that okay, draw the gate level circuit of this, you can easily do that, right? Because it's it is AND, these are AND, and this is a OR. Okay, this is a OR. So, and this is NOT, right? What is NOT? If you give A in a NOT gate, you get an A naught, right? And let's say if you want to do like, let's say A naught, B, C naught, you give 3 input in an AND gate. One is A naught, one is B, another one is C naught. So you get A naught, B, C naught. This way you can build these 3, right? A, B, C naught. Then A, B naught, C naught, and A, B, C naught, right? Then you can OR between these 3 signals, 3 binary signals, right? So since let's say if you have these 3 separately, like let's say you have this separately, then you can go ahead and give it to a OR gate. Okay, OR gate. The OR gate looks like this. You have a like this. This is yours, right? So I am not writing the full circuit here. Just to give you a heads up on the previous discussion. So let's actually draw the full circuit. How the full circuit should look like. Okay, for this expression, so that you get a brief revise of the previous concept that we previously discussed. So we need A naught, B, C naught. So let's actually think of this is A, this is B, this is C. Okay. So now we need this A naught, B, C naught. So we need an A naught. So let's say this is A naught, this is B naught, and this is C naught. Okay. Now draw the circuit here. A naught, B, C naught. So we need an A naught, we need a B, and we need a C naught. What is C naught? C naught is here. So A naught, this is the what? A naught, B, C naught. If I write it in a more linear way, let's think about it. So this is A naught, B, C naught. Then we have A, B naught, C naught. We have A, B naught, and C naught, right? I can do it, right? A, V naught, V naught, and then we have C naught from here. So we can take it, replace C naught from here. Okay. This is another AND gate. This is our A, B naught, C naught. Okay. Then we need A, B, C naught. How we can do it? We can have A and B, like A, you can take it from A here. We can take the B from here. A, B, and we have what? C naught. Where is the C naught? C naught is basically here. Okay. We have another AND gate. We have A, B, C naught. Now we make an OR between these three. OR. This is our Z. So any Boolean function can be done by this, right? Now we will go to a full adder circuit. At first, we will draw a truth table of it, of a full adder circuit, and from the truth table, we will show how we can express it in a Boolean function, and from the Boolean function, we can actually go ahead and make a gate level circuit from it. Okay. So in our full adder circuit, we have three input, right? Think about it. In our full adder circuit, how many inputs do we have? Three inputs. We have two inputs from the two numbers. For example, we want to add two numbers. Let's say like this, right? We want to add two numbers. We are calling this number A and this number B, and calling the output Z. Okay, for now. We also can express it in this way. The rightmost bit we can call it A0. Then the next one we can call it A1. Next one we can call it A2, and we can call it A3, right? Then our A0 is what? 1. A1 is 0, A2 is 1, and A3 is 1. Zeroth bit, one bit, like first bit, second bit, third bit. Then we have another number B, we can call it B0. Then we have a B1, then we have a B2, then we have a B3. Wait, B2 and B3. Now, when we add, okay, what do we have? For example, here we want to add one bit from the A and one bit from the B, and a carry from the previous bit, right? Carry means, think about it. If we add 1 and 1, we will get 0 and 1 here. This is not a part of A and B. This is part of the previous output. We are calling it a carry or carry in. Okay. So in our full adder circuit, we have two pins which comes from the A and B. Let's say we want to add in A0 and B0, or A3 and B3, and we also have a carry in from the previous bit. Remember, from the previous bit. And our output will give me what? Our output will give me something to put here. We are calling it a sum, and another bit to send to the next bit. We are calling it a carry out or C out. right? So by now you should be able to, if I give you a three binary bits here, for let's say 1 0 0 1 1 1, anything for these three, you know what is the sum and what is the carry out. So let's go ahead and so let's go ahead and draw the truth table for here. So I think I can erase this block for now. Already. Sorry, let's actually draw the truth table in the this is our way of doing a truth table. So these two are the output, right? Sum and carry out. We will begin our focus with one output. Let's forget about the second output for now. Okay. So if I add 0 0 0, what is the sum? 0. That means if I had 0 for the A and 0 for the B, and we have a 0 from the previous bit, what is the output? We have putting a 0 here and we are not passing any 1 for the last bit. And we can also think of this is 0, this is also 0, passed for the next bit. So sum is 0, carry is 0. Or you can think of it this way. Express the addition in a two binary digit number, which is 0 0. Then we have 0 0. Right? Let's say now we have 0 0 1. So 0 0 1. Then what do we have? 0 1. That means 1 for the sum and 0 for the next bit. Actually, we are not passing. 1 for the sum, 0 for the carry out. Now, 0 for the carry out. Now, let's say for the next one, 0 1 0. 0 1 0. Say, if it is 0 1 0, what happens? Sum 1, this 2 are same, right? If we have 0 1 1, if we have 0 1 1, the result is basically what? 2 in binary, which is 1 0, right? Now we have 0 at the sum and 1 at the carry out. 0 at the sum and 1 at the carry out, right? Now, if you proceed in a similar way, then we get 1 0 0 1 0 1. Okay. So this is the truth table for a full adder. Okay, full adder circuit. Now, if I ask you, okay, write the output sum in terms of the function of the input. Okay, write the function of this output. We have two output. One is sum and one is carrier. In terms of the inputs. This is what we are trying to do now. Okay. This is what we are trying to do now. Now we can do that, right? From our previous discussion, let's say forget about this. Forget about this column. Okay, forget about this. Just focus on this column now. And what have I told you before? We will only focus on the ones, right? We will only focus on the ones. So we have one here, one here, one here, and one here. 4 ones. So we need to write 4 ones. So to implement this one, what do we need to do? We need C naught, A naught, B, right? So we have C naught, A naught, B. Then what do we have here? The second one, C naught, A B naught, C naught, A B naught. So, okay. Now, what do we have here? C in A naught, B naught, C in A naught, B naught. And what's the last one? We have another one. This is C in A B. Okay, C A B. So this is the sum function, expression of the sum function, right? I hope you do not have any confusion with these notations right now, because it is and, the dots are basically and the plus signs are basically or. Just like we did it before. But actually, the function looks a really complex function. We can actually minimize the function or simplify the function a little bit. How we can do that? For example, we can take common between these two, just like we take common, right, in the in any function, right, mathematical function. So look at the first these two functions. We have C in naught as common. Then we have A naught B plus A B naught. Okay. Similarly, for the third and fourth function, we have C in as common. We can take these two. Then we have A naught B naught and A. So we have simplified the function a little bit. There was a really complex function. We have simplified the function a little bit. But actually, if you are familiar with Boolean functions, you readily know that this actually means something. This is an XOR function, right? A XOR B. So we can call it C in not into and A XOR B. Okay. Then we can go C in A XNOR B. This is the function of XNOR. Okay. Any question? Yeah, I'm just let me know if you have any question in the Google Classroom, probably any of you. If you need to be explained of any of these concepts, I think in our previous classes, at least a few times I mentioned this. What is XOR and what is XNOR? Please let me know if you don't get it. So now we have this function. It is a little bit more simplified. Now we can simplify it a little bit more. What is, so we have C in not A XOR B. C in A XOR B not. What is X not? X not is basically XOR and not, right? So we have a function not. So if you think about it, this is C in not, this is A XOR B. Now we have C in, this is A X not. That means the inverse of this. So we can write it this way: C in XOR of this whole thing. A XOR. Any question? So the simplified version of our sum is C in XOR A XOR B. Okay. Okay, so now I will go with I will talk about the C out. We have another output, right? Which is C out. If you remember, C out. Uh, so the audio is okay. Shall we just end it here and begin the video? So see, and I also need to take 5 minutes break. That's fine. So yeah. So it's the same way I have actually deduced the Boolean expression or the function expression of this sum. We can go ahead and do the same with the carry out. Okay. So how you can actually do the carry out? So now I've forget about this row. Okay, already about this. Now just focus on C out now. So we have one here. These four combinations we have one. So to make this one, what do we need? C in bar A B. Okay, write this down. C in bar A B. Then we have C in A bar B. Okay. Then we have C in A B bar. Then we have C in A B. Okay. So this is the Boolean expression of our carry out. And now, if we want to simplify it the same way we did for the previous one, how we can do that? So, one second. Actually, we can do it in a several way. We have several options of doing it. Yeah, we have several options of doing it. Okay. So what we can do is we can just take B as common. Then what we have? We have C in bar A plus C in A bar. Then we have B. Again, what we can do is we can take C in as scene A, then we have okay. So if you are familiar with Boolean expression, this basically means one, really. B or B1. That means B is 1 whenever B is 0 or B is 1, right? This function is 1 whatever below B you put here. So this vanishes because it is basically 1. So if this isn't 1, you make an AND with it. So it becomes basically 1. So in the next, you can just yeah. Okay. Now, one thing is, this is a simplified expression, but for the expression that you need to put it, we can actually simplify it in a different way. I will not go through the overall process now. So I will not go to the overall expression now. I will actually give you the expression like overall Boolean simplification in the classroom. For the interest of time, let's just keep it. This is one expression that we can use. Okay, but there is another expression where we have less of this not, because not you need to have inverter, right? So there is another way to simplify it, and you can easily do it just as an exercise. Keep it as an exercise. I will also provide it in the classroom so that you can match it with your result. So the cout is actually comes like this. Cout is A, B, B, C in, C in. This is the simplified expression. Basically A, B, B, C, C, A, and then N, B, so these are the simplified expressions of sum and cout. Now, if I erase the table, I will draw the two-letter circuit gate level layout. Okay. So if I have A, B, and C, A, B, and C in, then what do we have? If I do a XOR between these three, right? A XOR C in XOR B. So if you have a 3-input XOR, you can readily do this. This is the XOR circuit symbol. But if you have a 2-input XOR, not a 3-input, what you can do, you can do the XOR between the 2-input first, okay? 2-input first. For example, like this, A XOR B. Then XOR of A XOR B and C. You have what? A XOR B XOR C. This is our sum. Okay, this is our sum. This is our sum. Now we have A and B, B and C, C and D. So A and B. Then we have a, let's say, B and C in like this. B and C in another end. Then we have A and C. Okay. A and this is our C in. Yes, this is ours. Oh, have I drawn it wrong by the way? A, B. Then we have B, and what do we have here? Oh, yeah. I think there is a okay. Let's draw it from the beginning. So we have A and B. This is A and B. Then we have B and C in. Then we have A and C. Okay. This is A and this is C. Now we have A and B, B and C, A and C. Now if you make an OR of these three, we have A, we have this one. So this is basically this is what? This is A and B. This is basically B and C. Basically C and A. And here we have the area. So this is the block diagram of a full adder circuit. We have three input A, B, and carry in, and we have two outputs, sum and carry out. Okay. So this is how we can actually build a full adder circuit for 1-bit addition. Think about it. If we want to make a 1-bit addition, how many gates are we needing at? How many transistors each of these gate has? So it's not, if you think about it, it's overwhelmingly high number of transistors just for 1 bit, and our computers are calculating how many computations. So our processors have what level of computational capability. So you will know that we have, why we have this enormous number of transistors for computational purpose. Because as you know, this is just for 1 bit, and we will know that just to add maybe to 4-bit number, we will need 4 of these like cascaded with each other. So if we have one of these blocks, one of these full adder blocks, so this basically represents a block, a full adder block, which basically has 3 input and 2 output, right? What is the 2 input? Carry in A and B, and we have 2 output. One is carry out and sum. So if we have a block like this, full adder block like this, how we can actually use this block to build a multi-bit adder, okay? To build a multi-bit. So for example, we have two numbers. We have, let's say, number A and number B, okay? And number A, let's assume for now all of them are 4-bit number. So we have 4-bit. Okay. So what we want to do? We want to add these two. Add A naught and B naught. So let's draw a full adder. So for simplification, I am just writing FA. Okay, FA. And in our full adder, we have carry in and 2 other pins, right? A and B. And we have carry out and sum here. Now, for adding A naught and B naught, I am giving A naught here and B naught here. Since it is the least bit, rightmost bit, we do not have a carry, right? So I am just putting a 0 here. Now, this gives us what? A sum here, which is a 0. We get a 0, and we have a carry. And this carry will be passed by C1 as the next bit, next full adder. So I will just draw another full adder block here. And in this full adder block, we have a carry in input. I connect the carry out from this directly to where? The carry. Okay. Then we have another two pins like this, A and B. So for the next bit, I will put A1 and B1 here and add to the carry the previous bit, and this will generate a sum which is here, which is S1, right? And the carry out will pass to the next. This is how we will build a 4-bit uh, 4-bit adder set. Okay. Now, if we have a block like this, then A2, B2, S2, okay. Then the next block will just follow. S3, S2, S3. Now, think about it. The last carry, the last bit, here a carry will be generated, right? This carry will be directly sit here, right? Whatever carry we have here, we do not have any AB for the next bit, right? This is zero, basically 0, 0. So this carry will be directly to S5. So this carry out is basically directly S4. Sorry, yes, the fifth bit or the fourth digit S4. So this is S4. Okay. So this is the design of a 4-bit adder circuit. Okay. And these of you already know what this full adder block means. Okay. What this full adder block means. So in your assignment or homework, you will build a full adder block like this. In Spice, which is a free software. I will now show how you can install if this free software LD Spice. And in that LD Spice, your job to simulate this circuit. Okay. So I hope you can see my screen, and in your browser just search LD Spice. If you have Chrome, let's see. Yeah. So in your browser, just search LD Spice, and if you will directly, I think, go to a link where you can download the LD Spice Windows version and Mac version both. I hope you can see my screen now. So I'm just downloading the Windows version since we have Windows here. And you see that the download is progressing. So this is basically a very handy tool, handy free software where you can draw and simulate the circuit. So just double click on the installer. I think it will directly accept the license agreement and just install this. Yeah. So this is a very good software. You have a lot of free libraries that you can use. This software is completely free. That's the best thing. You don't have any access like you need for the other advanced softwares. Yeah. So if I want to launch it, you'll see that LT Spice is launched. Yeah. So this is the LT Spice interface view that you should pop up when you launch LT Spice. For a new circuit, just go to File and select New Schematics. Okay. Then you will see a blank grayish window will pop up, and here actually you can draw your circuit. Okay. So at the top panel, you see there are a lot of components like wire, ground, voltage source. These are familiar components that you can actually use. And I will actually advise you to get your hands on it first, like simulate small circuits first. And once you do that, I think it will be better for you to move to much bigger circuits. Okay. Now let's actually draw a transistor, it's an inverter, let's say, where we have PMOS and NMOS. So for actually getting any component, you go to Edit and Component here. Okay. You can also, I think there is a, one second. There should be another option where you can directly go to the component window, but since we already know, like if you just click on the component, you see there are a lot of options. If you click any of those, you see the component symbols, right? And you can navigate these components. Now, I will just use a PMOS and NMOS to build an inverter, okay, for now. Don't get confused if you find the symbols a little bit unfamiliar. These are basically the same symbol. The symbol in the middle, the arrow in the middle is basically the body terminal or the substrate terminal. So we have source, drain, and gate terminal as they are in the normal symbol, but we have another body terminal. So I'll tell you what you should do with your body terminal when you actually simulate a circuit. So let's take the NMOS and place it somewhere. Okay. And then let's take a PMOS and place it here. So for an inverter, we have PMOS and we have an NMOS. So for drawing a wire, you should just press W, okay? If you press W, you see that this cross navigation, the mouse becomes like this, it becomes a cross. Now, or you can just go to the wire, okay, and draw a wire. So double click on any of the places and press escape. You see? So if I want to draw a wire, let's say from this gate to this gate, I just draw it normally and double click on it and escape. Okay. Oh, I think the gate terminal ends here. I'm sorry about it. So go to undo, edit, undo. Now draw this again. Yeah, I think you don't have to give an escape. There is just click on it. Just click on it. It will do. Okay. Now I want to draw the VDD and ground. So we have a voltage source here. You can take the voltage source from here. You can also take the voltage source from the edit window. Okay, from the edit window. For example, you can go to edit and go to components. You will find the voltage sources here as well. But I think this is the most convenient option. So keep a voltage source here. Now draw a wire. You need a ground. Place a ground here. Actually, this is a very easy tool for you to learn. Probably the best tool available. So we have given a high voltage here and always don't forget to connect the negative terminal of the voltage VDD with the ground. Now we have to give an input and the output, right? An input and the output. Where should we place the input? Here, right? So how we can do that? We can go to the component again. Not component. You can take the voltage source from here. And don't forget to connect the negative terminal of your voltage source with any voltage source with the ground. Okay. Now make sure that you are giving the right input voltage. For example, for your VDD, okay, for your VDD for these transistors, for now, just right click on it. You see a panel will open, and here actually you can give an input. Okay. So what you can do, you can click advanced. Then you will see a very detailed customization window will pop up where you can actually give a lot of where you have a lot of options as your voltage source. For example, pulse, sinusoidal wave, exponential wave, and in each of these you have other parameters that you can play. For this source, it is basically a DC source. It is VDD. So we are giving a DC voltage here, for example, 5 volt. Okay, constant 5 volt. That means it doesn't change with time. It is VDD. But for the input, we need a pulse. Remember, it is an inverter. So inverter gives a 0 when the input is 1. When the input is 1, inverter gives a 0. And what does 1 mean? 1 basically means high voltage. So we will give a pulse. So we see both the cases for both 1 and both 0. Okay. That's what our target is. That's why we will give a pulse here. So go to right click on it and go to advanced. Then we will go to pulse and initial voltage 0. Our on voltage is that's a 5 volt. And keep the delay as 1 micro. The rise time also 1 micro, fall time also 1 micro. And on time keep it 10 micro and period keep it 20 micro. So we have given a pulse which is 20 micro, which has a period of 20 micro with 10 micro of on time. That means 10 micro it will give 5 and other 10 micro it will give what? 0. And not 10 micro actually, we have a rise time and fall time delay time. But this is roughly. Okay, this is rough. And give a okay. Then you see that this details will be there. Now, one thing is your body terminal. So you have a body terminal, right? So connect the body terminal with the PMOS to the VDD and connect the body terminal of the NMOS to the ground. Always do that. For larger circuits as well, if you have a circuit that has a wide number of transistors, please do the same. Connect the body terminal of the PMOS with the VDD and the body terminal of the NMOS to the ground. Always do. Of all the transistors. Now we want to run a simulation. For running a simulation, you go to the simulate tool and then run. If you click on it, it will actually show you a window where you can actually select different level of analysis. I have already discussed in class what transient analysis means, what DC sweep means. At least you are familiar with these two type of analysis. Transient means you want to see the currents, voltages, and other parameters in terms of time. So in an x-axis you have time. So remember, we actually gave a pulse at the input. So we want to see in terms of time. So when the input gives me 1, what the output gives. When the input is 0, what the output is. So in the x-axis we will have time, and in the y-axis we will have the values of the inputs and outputs. Okay. So that's why we will go with the transient analysis, and our stop time will be what? Remember, we have a period of 20 micro. So let's say we want to stop at 40 micro, 2 period. Okay, let's just select it for now. The maximum time step is basically 0.01 micro. For now, it is basically the time step that the simulation will take into account for each point. So the simulator will actually evaluate its inputs, outputs for different points, right? If you give it like very small, it will actually give you a smooth curve and also take a lot of time. But if you give a very high value, for example, if I give 1 micro instead, it will be really fast, but the graph will not be smooth, as you can guess. So let's, for now, 0.1 micro is fair enough. Just click OK. Okay. Okay. Okay, I mistakenly actually given it a pulse in the VD. Okay, now a window will pop up. You will not see any graph here. Okay, you will not see any graph. Why? Because you have not selected what it should plot, right? You have not told it that okay, plot this, but you only told it to run it for 40 micro. 40 micro for what? I want to know the input. If you click on it, you see you see the input. Remember, we have given it a pulse of what? 20 micro. With 1 micro rise, 1 micro fall, and 20 micro. So roughly 20 micro, right? Now we want to see the output as well. If you click on the output, yes, you can see that we have a inverted output. Let's change the color so that it is more visible. I don't know. I think it is more visible now. So as you can see, for when we give an input as 1, we are getting a 0 as the input. When we are getting the giving the input as 0, we are getting a 1 at the output. Okay. So this is how you can actually simulate any circuit. Okay. Now using this simulator tool, you can go ahead and try to simulate other gates as well. For example, NAND gate, NOR gate. Okay. And I'm giving you an assignment this class actually, where you have to simulate a complete full adder block. Okay, a complete full adder block. So follow the same procedure. you already know the circuits, transistor level circuits, and you can easily do that. It's really easy to use. So let me actually write down what your assignment is going to be. I will also upload the assignment on the Google Classroom, so you can see that assignment. But in your assignment, you will basically build a 4-bit full adder. You don't have to actually simulate the full 4 adder here. You just have to simulate one block, 1 bit full adder. So let me actually write it down for you in the board.
It was simply exporting the flat.
So in your assignment, what you will do, you will basically simulate a 2-input XOR gate in LT space. You already, I think, have I have discussed the schematic, circuit schematic, transistor level schematic of the XOR gate, simulated in LT space. So what your input and what you should have in your assignment is at first the circuit circuit schematic. Okay, at first you have to at least give the circuit schematics that you have built. For example, the whole circuit picture. Then you have to provide the simulation parameters, like what input you are giving, what kind of pulses, what is its period, the parameters, the simulation parameters, and simulation waveforms. Okay, simulation params and simulation waveforms. Okay, now what's the simulation waveforms will give you? The simulation waveforms will have actually three, for example, for a 2-input XOR, you have 2 input and 1 output, right? So in your waveform, you should give 2 pulses, okay? Let's say you have an XOR gate like this, X and Y and Z. For the X, Y, let's say you give 2 pulses. One is like this, and for the Y, you give this. A pulse with half the input. Okay, I'm just giving you an idea. For the Z, you should get something uh, like this. You should get one like this. This is the solution from XOR, right? You already know. Like when we have 1, 1, you have 0. When we have 1, 0, you have 1. When we have 0, 1, we have 1, and when we have 0, 0, we have 0. So this is the simulation waveform of Excel grid that you should provide in your what? In your assignment submission. And for the second one, for the full adder circuit, how many inputs do you have? Think about it. You have actually 3 inputs. Right. So in your adder circuit, you should have 3 inputs and 3 waveforms like this. So you have carry in, you have A and B. So your carry in should be like this. And your B should be half of this. Okay. And you sorry, and your B should be more half, like half of this. So like this. I am just trying to articulate what it should have. Okay. Then in the output, for example, you have 2 outputs, sum and carry. You will now have all the possible input combinations. So these are the 2 assignments. I already told you to do the assignment in the previous week. I also will upload the assignment in Google Classroom probably today. Yeah, that's it. So thank you everyone. Please feel free to ask any questions if you have in the Google Classroom or contact with us. Hope to see you in the next class. Thank you.